In this video, we'll review what we've learned so far about periodic motion and simple harmonic motion in particular, and then we'll look at energy in simple harmonic motion. So let's review what we determined in our last video. Importantly, what we found is that a mass oscillating on a spring, whether it's oscillating vertically or horizontally without friction, the period of the oscillation will be the same, and it will be given by the equation t is equal to 2 pi times the square root of m over k. Let's talk about that result. First of all, notice no amplitude in formula. So whether I displace the mass 1 centimeter or 10 centimeters and let it go, the period will be the same. Now, why is that? Well, remember that the greater displacement, the greater that restoring force. And so what we find is that when we pull that mass and let it go from a greater distance, the force is going to be greater, and therefore the acceleration of the object will be greater. So it will be able to cover a greater distance in the same amount of time. So the period does not depend on the amplitude. Notice that even if we're talking about a spring hanging vertically, it also doesn't depend on the acceleration due to gravity. So no g in the formula. And then what we see is that the period is directly proportional to the square root of the mass. So if I quadruple the mass, the period is only going to double. Also notice that the period is inversely proportional to 1 over, or inversely proportional to the square root of k, I should say. So that if I increase the spring constant, meaning it's a stronger spring, that will decrease the period, but it's as the square root of k. Let's look at the position, velocity, and acceleration versus time graphs for simple harmonic motion. Remember that when we were trying to figure out what equation describes simple harmonic motion, we were solving that differential equation, and we saw that either sine or cosine would work. The reason that we picked cosine was because we want our object to be at its maximum displacement at t equals 0, because we know we're going to displace the mass, and then when we let it go, it's going to start from that maximum displacement. And that's why we choose cosine. You'll notice, therefore, that our object starts at t equals 0 at a position x equals a, which is the amplitude. And it's going to oscillate between there and negative a. Remember that this will be one period where we found that the period for simple harmonic motion is 2 pi square root of m over k. Now, to figure out what the velocity is as a function of time, we know all we have to do is take the derivative of x with respect to t. When we do that, we get negative omega a sine omega t. Therefore, the velocity is going to oscillate between a maximum value of omega a and a minimum value of negative omega a. Those are important to remember because in some problems you'll be given the maximum velocity or the maximum acceleration. So notice that since sine just oscillates between 1 and negative 1, the biggest that v can ever be is just omega a. And so that corresponds with the way we've labeled our graph. Notice too that the velocity makes sense. If the object starts out to the right of the equilibrium position in the positive direction, then initially, the instant I let it go, it's not moving, but then it's moving to the left, and so our velocity is negative. And notice it's a negative maximum as the object passes through equilibrium. When we get to the other extreme, that's where the velocity is instantaneously 0. Coming back through equilibrium, notice that the velocity is a maximum at equilibrium. Let's look at the acceleration. Again, we know that the acceleration is just the derivative of velocity with respect to time. And so we end up with a negative cosine. That makes sense as well, because if you think about when the object is displaced to the positive direction, the force is in the negative direction, and we know the force and the acceleration, the net force and the acceleration, are always in the same direction. So when the displacement of our object is a maximum positive, that's when the acceleration is a maximum negative. Also notice that at equilibrium, when the object's at equilibrium, well, that's where the spring is not stretched or compressed. Therefore, net force is 0, acceleration has to be 0. Notice that the maximum value for the acceleration is just omega squared a. So we would label that omega squared a and negative omega squared a. So we've now got our solution for what the position, the velocity, and the acceleration look like as a function of time. Again, clearly the acceleration isn't constant. That's why we had to go through this more complicated analysis. We couldn't just use kinematics. Why don't you pause the video and do the following problem for me. It says a 0.5 kilogram mass is attached to a spring with a spring constant of 22.5 newtons per meter. What are the angular frequency, the frequency, and the period of the motion? Okay, in order to solve this problem, the first thing we have to remember is that the angular frequency is equal to the square root of k over m. Therefore, in this problem, we've got the square root of 22.5 divided by the mass, which is 0.500. Do the square root there, and we get a value of 6.71. Now, what are the units of angular frequency? The units of angular frequency we write as seconds to the minus 1. Now, you might say, but isn't something per second, isn't that what we mean by hertz? And you'd be correct, but we reserve hertz for regular frequency. Angular frequency, therefore, has units of seconds to the minus 1. Now, once we have the angular frequency, we can find the frequency. We know that the angular frequency is 2 pi times the frequency, so therefore the frequency is the angular frequency divided by 2 pi, or 6.71 divided by 2 pi. And we get 1.07 hertz. By the way, let me point out one of the most common mistakes that students make on exams. When they plug this into their calculator, they forget to put in the parentheses. Okay, so I'm just going to write, watch out. Because if you just do 6.71 divided and then put in 2 pi, what your calculator is going to do is it's going to divide by 2, but then it's going to multiply by pi. This is where always take a second to think about the answer. We know that 2 pi is a little bit more than 6. So if we have a number that's a little bit more than 6 and we divide by 2 pi, we should get something pretty close to 1. And so it makes sense. Also, again, for frequency, our unit is the hertz. Last, we were asked to find the period. Period, we know, is 1 over the frequency. So it's 1 over 1.07, and that would be 0.937 seconds. And of course, you could have calculated it directly from the information given, knowing that period is 2 pi times the square root of m over k. Most importantly, remember, period does not depend on the amplitude. So we didn't need to know what the amplitude was to be able to figure out what the period is. Okay, why don't you go ahead and pause the video and continue with this problem. Okay, let's see how you did. First of all, make sure that you have your calculator in radian mode, because if you're not in radian mode, you're not going to get it right. Okay? So in these formulas, notice we're not using degrees, we're using radians. Here we're asked to figure out where the object is at a time of 2.5 seconds. And we've been told the initial distance that the object was displaced from equilibrium is 0.1. So the first thing we have to realize is that we were given the amplitude. So the amplitude is 0.100. Now I just need to plug into my formula for the position as a function of time, a cosine omega t. So we have 0.100 times the cosine of 6.71, which is our value for omega, times the time, which is 2.50. And when I calculated that, I got negative 0.0483 meters. Notice I'm being careful with my sig figs here. Everything is to 3 significant figures. You'll also notice that where the object is right now is it's about halfway to the farthest point it goes to the left. So in other words, we know that the maximum displacement to the left is negative 0.1. It's about halfway there. So our mass is right about here. The next question is, what is the maximum velocity the mass will have? So not at any time, or not at a particular time, but at any time. What's the fastest the object ever goes? Again, our formula for velocity is negative omega a sine omega t. And as we just discussed, that means the biggest that v can ever be, v max, is just omega a. So I can go ahead and plug in my values, 6.71 times 0.100, and I get 0.671 meters per second. Lastly, we're asked, what is the velocity at 2.5 seconds? Notice, by the way, so far we know the object is here, but we don't know if it's on its way back to equilibrium or if it's still on its way to its maximum negative displacement. Well, we'll find that out here. V is equal to negative omega a sine omega t. So we can go ahead and plug in those values. Omega a we've calculated to be 0.671 times the sine of 6.71 for omega times, again, the 2.5 seconds. And what you should end up with is that v is 0.588 meters per second. So now we know not only is the object right here, but that it's on its way back towards equilibrium, since the velocity that we got was positive. Let's look at energy in simple harmonic motion. First of all, we know that delta k plus delta u is equal to WNC, the work energy principle. But in this case, we're looking at simple harmonic motion when there is no friction. Also, there are no applied forces. So what we get is delta k plus delta u is equal to 0. And in other words, what is happening is that there's a constant interchange between kinetic energy and potential energy as the object moves back and forth. So for example, we know when the object is at A or negative A, all of the energy is stored in the spring because the object is momentarily at rest. When the object is passing through equilibrium, we know that all of the energy is kinetic energy because the spring is not stretched or compressed. But at any point in between those extremes, we know that we have a mix of kinetic and potential energy. So let's go ahead and figure out how we could calculate the potential energy and the kinetic energy at any time. We know that the potential energy of a spring is 1/2 kx squared. We also know that kinetic energy is 1/2 mv squared. But for simple harmonic motion, we've determined that the position as a function of time is a cosine omega t, and the velocity as a function of time is negative omega a sine omega t. So we can actually just plug these into these formulas. In other words, if I want to know the potential energy at some time t, all I have to do is do 1/2 k times a cosine omega t, and that quantity squared. That would give me the potential energy at a particular time t. Or U is equal to 1/2 k a squared cosine squared omega t. Now, if I want to know the kinetic energy at a particular time, I can just plug in what we know the velocity is, 1/2 m times negative omega a sine omega t quantity squared, or the kinetic energy is 1/2 m omega squared a squared sine squared omega t. Now, you'll notice that what's in front of the potential energy and what's in front of the kinetic energy are different. However, I want to show you that they're actually the same thing. We know that omega is equal to the square root of k over m. Therefore, omega squared is k over m, and omega squared times m would just be k. And therefore, you'll notice that m omega squared a squared is the same as k a squared. Okay, so those terms are actually that are in front of the sine or cosine are actually the same. All right, so we now can figure out what the potential energy is at a particular time and what the kinetic energy is at a particular time. However, from conservation of energy, what has to be true when I add the potential energy plus the kinetic energy at any time? Well, the answer is it better be a constant, because the overall energy can't change. So let's just see that the math agrees with that. The total energy should just be equal to the potential plus the kinetic, and that total energy should not change. Remember, when we write delta k plus delta u is equal to 0, another way to write that is k minus k naught plus u minus u naught is equal to 0, or k plus u equals k naught plus u naught. In other words, the total energy doesn't change. So let's see that the math shows us this. Notice that I can factor out 1/2 k a squared from both of these terms. And what I'm left with inside the parentheses is cosine squared omega t plus sine squared omega t. Well, hopefully you remember from trigonometry what cosine squared plus sine squared is equal to. It's just equal to 1. And therefore, what we've shown is that the total energy is equal to 1/2 ka squared. And that total energy doesn't change. Notice, by the way, that that makes sense, because really this comes from the fact that when the displacement is equal to x, or when the displacement x is equal to the amplitude, that's when there is only potential energy. So that's the total amount of energy the oscillator starts with. I could also write the total energy as 1/2 m omega squared a squared. The reason for that, remember, V max is omega a. So all we're saying here is the maximum kinetic energy as it passes through equilibrium. Well, that's when the potential energy is 0, so that also has to be equal to the total energy. Let's take a look at the following problem. A 0.5 kilogram mass oscillates on a spring with a spring constant of 28 newtons per meter. If the total energy of the oscillator is 0.6 joules, what's the amplitude of the motion, and what's the kinetic energy at 2 seconds? Why don't you go ahead and pause the video and try this yourself and see if you get it right. Okay. We've said that the total energy is equal to 1/2 ka squared. You'll notice in this problem we've been given the spring constant and the amplitude. or sorry, we're trying to find the amplitude. We've been given the total energy and the spring constant. So we should be able to solve that for A. So taking that equation and solving for the amplitude, I get the amplitude is 2 times the total energy divided by the spring constant, all under the square root sign. And so I get the square root of 2 times 0.600 for the total energy divided by 28.0 newtons per meter. If you solve that, you should get that the amplitude is 0.207 meters. Now, we're next asked to figure out what is the kinetic energy at a particular time of 2 seconds. And I should have 3 sig figs there. We know that the kinetic energy as a function of time is 1/2 Ka squared sine squared omega t. Again, make sure that you don't get confused by the k's. That k is spring constant, as is that one. Big K, or capital K, remember, stands for kinetic energy. So I can go ahead and plug in the values here. We have 1/2 times k, which is 28, times the amplitude, 0.207 squared, times sine squared of omega t. Now, we actually don't have omega yet, so let me go ahead and just calculate that. Remember, omega is the square root of k over m. And when I worked that out, I got 7.48. Remember, the units of omega are seconds to the minus 1. Therefore, 7.48 times 2.00 is what goes inside there. Again, make sure that you are in radian mode. And if you are, you should find that the kinetic energy of this object when it's been moving for 2 seconds is equal to 0.278 joules. That's going to end our study of simple harmonic motion. As you take further courses in physics or engineering, you'll look at simple harmonic motion again. You'll look at it with more complexities like friction involved and what we call damping. But also, simple harmonic motion is the foundation for something that we'll talk about in our next physics course, which is waves. So anything that's vibrating creates waves. If you think about how your vocal cords create sound waves, they're vibrating in your throat. Or if you hit the string of a guitar, you cause that string to vibrate, or the string of a piano, and those vibrations create sound waves. So understanding simple harmonic motion is a key to being able to understand how waves are created and how waves behave. And again, that term harmonic that we've used here, when we talk about waves in the next course, we'll see how that relates to harmonics in music.